Hello, my dear friends. I am Eldar Zeynalov from Azerbaijan National Academy of Sciences. Would like to greet all of you and hope that my report will find you in good health and state of high spirit. Title of my report is Metal Carbon Nanocatalysts in the Aerobic Peroxide Oxidation of Decahydronaphthalene. This topic has significant background. The oxidation of hydrocarbon is considered as a process of the present day, exemplified by a number of advantages in terms of modeling, nature-like technologies, and industrial ecology. That statement is correct and reflects the growing interest in the using hydrogen peroxide for the oxidation of hydrocarbons. Hydrogen peroxide is often considered as a green oxidant in chemical processes, especially when compared to traditional oxidizing agents. Its use is linked to nature-like technologies in industrial ecology due to several key advantages. The main byproduct of hydrogen peroxide is water, which is benign and environmentally friendly. This contrasts sharply with many other oxidants that produce toxic or corrosive waste materials. While concentrated hydrogen peroxide requires careful handling, it is generally considered safer to transport and handle than gaseous oxidants, like molecular oxygen or air at high pressure or highly corrosive liquid oxidants. When used with specific catalysts, often based on transition metals or zeolites, mimicking natural enzyme systems, hydrogen peroxide can achieve high selectivity for oxidizing a CH bond in a hydrocarbon. This is a crucial aspect of developing nature-like or biomimetic processes as a natural enzymes, like cytochrome P450, perform highly selective oxidation under mild conditions. Mild conditions. Many hydrogen peroxide based oxidation system can operate under relatively mild conditions, that is, lower temperatures and pressures, which saves energy and can improve process safety, contributing to industrial ecology. This combination on environmental compatibility, selective chemistry, and potential for mild operation make hydrogen peroxide a significant reagent for developing sustainable and efficient nature-like technologies in the chemical industry. Follow this framework, the liquid phase non-catalytic and catalytic aerobic peroxide oxidation of decahydronaphthalene, that is decalene, was undertaken. The combination of aerobic uh, with involving of molecular oxygen and peroxide, that is hydrogen peroxide or organic hydroperoxides, suggests a process where the peroxide is used either as a primary oxidant or more commonly as an initiator in the presence of uh, uh, molecular oxygen or air. In the case of catalytic reaction, iron containing multiple carbon nanotubes obtained by pyrolysis, produced by pyrolysis of hydrocarbon feedstock, cyclohexane, in the presence of ferrocene as precursor catalyst, followed by chemical vapor deposition were used as a catalyst. Next slide represents the laboratory pyrolytic setup constructed and compiled in the laboratory and used for CVD synthesis of multiple carbon nanotubes. The details of the method for obtaining of metal feed carbon nanotubes are followed. Precursors. Ferrocene acts as a catalyst. Precursor, source of iron, ferrum, and provides some carbon. Upon heating, pyrolysis, it decomposes into ferrum nanoparticles. Cyclohexane acts as primary hydrocarbon feedstock, that is, carbon source. At high temperatures, about 800 to 900 Celsius, ferrocene and cyclohexane are vaporized and introduced into the reactor. The ferrocene pyrolysis thermally decomposes to form highly active uh, iron nanoparticles, which act as catalyst seeds. The cyclohexane also pyrolyzes to release carbon atoms or reactive hydrocarbon fragments. The carbon atoms adsorb onto the surface of the ferrum nanoparticles, dissolve into the iron, and saturate the particle. Once supersaturation is reached, carbon is deposited out the particle as a tubular sp2 uh, gibrit, gibritizide graphite structure, forming multiple carbon nanotubes with the ferrum nanoparticle often remaining encapsulated in the tip or base of the tube. Tip or base growth mechanism. Thus, the final ferrum containing multiple carbon nanotube structure is formed. The iron nanoparticles encapsulated within carbon nanotubes are thought to enhance the electron donating properties of the nanotubes walls, which is favorable for electron transfer during the oxidation process. Slide 6 and 7 present same images, and slide number 8 results ADX analysis of the elemental composition of the being synthesized ferrum containing multi-walled carbon nanotubes. It is seen from this snapshot the accordance of carbon nanotubes in shape and size to the standard requirements. Slide number 6 and 7. The size diameter of the carbon nanotubes uh, are about 44, 52, and 43 nanometers. That is good in match with standard requirements. As for elemental composition, the content of carbon, iron, and oxygen are prevailing to consist major components of multi-walled carbon nanotubes. Next slide is general view of catalytic oxidation of hydrocarbon in the presence of uh, carbon multiple carbon nanotubes. Catalytic application of ferrum containing multiple carbon nanotubes is often ferrum containing multiple carbon nanotube is often used as a catalyst for the liquid phase aerobic oxidation of hydrocarbons, notably for the oxidation of decalin in our case. The goal is to produce valuable oxidation products. Next slide, the schematic diagram of the laboratory setups for oxidation of liquid hydrocarbons. The first version of laboratory setup is on the left side and is used for the aerobic peroxide oxidation of liquid hydrocarbons. This is the simplest setup where temperature regulation is done by circulating liquid. In this unit, total oxidate data can be obtained without separated from the readily boiling reaction products, condensate. The second unit allows the oxidation products to be fractionated into two parts, oxidate and condensate. The temperature is in the reactor is regulated by an electric winding. Slide number 11 shows the aerobic peroxide oxidation process itself of a mixture of decalin isomers in the presence of metal carbon metal containing nanocarbon catalyst. It shows the formation of hydroxyl radicals, which formed by decomposition of hydrogen peroxide, and the radical and its radical attack to the hydrocarbon substrate, and the redox cycle between the radicals in the metal and the electronic exchange between the liquid and solid phases. On the right side, real laboratory setup, working laboratory setups adjusted for making experiment. Characteristic parameters of oxidation products where acid number and active oxygen index in oxidating condensate were correctly applied. Slide 12 and 13 demonstrate respectively the acid number and active oxygen index values measured in the oxidate and condensate during aerobic peroxide oxidation of decalin alone. The reaction duration is 3 hours. The amount of hydrocarbon is 50 milliliters. During the reaction, the sequence of formation of oxidation products was traced, and it was found that maximum formation of carboxylic acid at a fixed reaction time falls at 130 degrees Celsius. The acid number determination was made twice using aqueous solution of potassium hydroxide and using aqueous alcoholic solution. The latter possesses more capacity to dissolve the oxidation products, and therefore it gives the higher values of acid number. Slide number 14 show graphical pictures of the acid number deviation depending on the reaction temperature. The acid number values in the oxidate and condensate during decalin oxidation with hydrogen peroxide at 130 degrees Celsius without a catalyst and in the presence of the ferrum containing multi-wall carbon nanotube catalyst show the results consistent with hydrocarbon aerobic oxidation products sequence which well known from the existing theory. The experimental results show that during 3 hours of oxidation, the acidic components of the oxidate are converted to acid components much more actively than in the case of oxidation without catalyst. The catalyst loses its activity during the first round, and the parameters of oxidate and condensate decrease significantly when the catalyst is used again. This case requires further more careful, without any doubt, requires further more careful experiment with the carbon nanocatalyst of different morphologies containing variety of transition metal. Next slide is this infrared spectra of products of aerobic peroxide oxidation, non-catalytic and catalytic oxidation of decalin at 130 degrees, and for oxidate, the absorption bands of the symmetric, asymmetric, valence and deformation vibrations of the oxygen containing group bonds are clearly seen from the spectra. Characteristic absorption bands of the aromatic rings at, at the region near 1,400 reciprocal centimeters and valence vibration of CH bond of alkanes and cycloalkanes in the region 2,900 reciprocal centimeter are also observed. This slide is data of results of chromatomass spectroscopic analysis showed the formation of a following number, a wide range of different oxygen-containing compounds. These are unsubstituted, alkyl substituted, and cyclic saturated, unsaturated, and aromatic hydrocarbons as well as primary aliphatic, alicyclic, and aromatic alcohols, aliphatic and alicyclic ketones and aldehydes, aliphatic, alicyclic, aromatic, and oxy acids, and different aliphatic esters have been found in the oxidate. Despite hydrogen peroxide, the conclusion is despite hydrogen peroxide is a hydroxylating agent, the influence of air oxygen as co-oxidizer allows to bring the reaction to the stage of acid formation. Total conversion of initial decalin is about 78, 80%. And content of acid reach 16 20% weight percent. That is has been concluded the JCMS spectrum that from is has been concluded from the GSMS spectrum that the chain reaction of oxidation of decalin proceed with destruction of the framework of the naphthenic cycles and with concomitant by processes of oxidative dehydrogenation, functionalization, and alkylation of intermediate molecular fragments. The general core and proposed mechanism of the catalytic stage for the aerobic peroxide oxidation of decalin in the presence of ferrum containing multi-walled carbon nanotubes are depicted in slide number 19. This is decomposed of hydrogen peroxide to form initial highly reactive hydroxyl radicals, which then abstract hydrogen atom from decalin to form decalin radical. That is related to the mechanism of the oxidation. The decalin radical quickly reacts with molecular oxygen to form a peroxyl radical. This peroxyl radical uh, Peroxide radical is the main chain carrying species and abstract of hydrogen atom from another decalin molecule to form primary oxidation product, and then reaction will and reaction is going at the stationary stage. The catalyst typically transition metal salt engage, embedded, and enrolled by multi-walled carbon nanotubes dramatically changes the mechanism of participating in the decomposition of the peroxide through the redox cycle. The catalyst activates the peroxide to efficiently generate radical, which accelerates the initiation and propagation steps of the oxidation. Conclusions. For aerobic peroxide catalytic oxidation of decalin in the presence of ferrum containing multi-walled carbon nanotubes, the Fenton-like catalysis of hydrocarbon oxidation is established. In this process, the active centers of oxidation are iron ions embedded on the active nanocarbon carrier. It has significant advantages due to more active exchange transfer of electrons from the metal to the substrate promoted by the core of multi-walled carbon nanotubes. Oxidative aerobic peroxide conversion of decalin occurs with the opening of molecular naphthenic rings with concomitant formation of a wide range of different compounds, like linear and cyclic, saturated and unsaturated hydrocarbons, primary alcohols, aliphatic and alicyclic ketones, and aldehydes, fatty naphthenic and aromatic monocarboxylic acid, and also different aliphatic acid. Despite the auto-oxidative nature of the reaction, the yield of non-carbolic acid is significantly high, about 20%, which can be used for targeted processing of complex hydrocarbon feedstock. Thank you for your attention. I wish you all success and prosperity. Special thanks to the symposium organizers and to Professor Tamara Tatrishvili for the opportunity to participate in this wonderful event. Goodbye, my dear friends.